This video is on our Introduction to Polynomials, section 14.1. Our learning targets are we're going to write a third degree equation, that means a cubic equation, that represents a real world situation. And we're going to graph a portion of this equation and evaluate the meaning of what we call a relative maximum. Okay, so here's our setup. So you can imagine a cylindrical package, something is being shipped for a company. They want to put some items in a cylindrical package. The height of the package plus 3 times its radius cannot exceed 50 inches. Ultimately here, as we scroll down here, we're going to be asking the question, what's the maximum volume? Write a function and find the maximum volume. So we're going to start out here with just write an expression for the height based on what we know here. Okay, so it says here that the height of the package plus 3 times its radius cannot exceed 50. And since we're dealing with volume and we want to look at the maximum only, we're not going to write an inequality, although the sentence kind of lends itself to inequality, cannot exceed 50 inches, so that means less than 50 inches. But we're going to be looking at the maximum, so we're going to set it equal to 50 inches. So the height of a package, h, plus 3 times its radius, r, equals 50. Okay, so that means if we take the height and then 3 times this radius here, we want it to equal 50. Okay, now since it says write an expression for h, at this point we want to go ahead and solve this equation for h. Let's go ahead and do that. So we're going to subtract 3r from both sides. And we got our expression for h. It's h equals 50 minus 3r. We're going to use that fact in just a second. Okay, now our next task is to write a function, v of r, for the volume of the tube in terms of r, the radius. So let's just kind of think about the volume of a cylindrical package here for a second. So the volume is given by the area of the base, which is a circle, so it's pi r squared, times the height. So what we're doing is finding the area of this circle and then multiplying it times the height. So that's the volume equation that we're going to use. Now the problem with this is that we have 3 variables going on here. We have v, we have r, and we have h. There's no way for us to graph that or to analyze it or to use a maximum based on 3 variables. So we're going to have to make a substitution here. And the substitution we're going to make is based on our last screen there where we solved something for h, if you remember that. Okay, so I brought over our expression for h here. We found h equals 50 minus 3r. And we're going to make a substitution right up here for h, because that's what it told us to do, is to write a function v of r. So the volume and only r in our equation. So right there, we're going to bring this piece over because it's connected to the problem setup. That h and the r are related based on our last work where we wrote the expression h equals 50 minus 3r. Okay, so let's just bring down the rest of our equation here and we'll have our function. So v of r equals pi times r squared times 50 minus 3r in parentheses. And it's important that we keep that substitution in parentheses because we have multiplication going on here between the pi r squared and that. Okay, so that's our function. We've written our function v of r equals pi times r squared times the quantity 50 minus 3r. And this lives under the constraints that we originally set up, which is up top here. Remember, it says that the height of the package plus 3 times its radius cannot exceed 50 inches. Okay, so we're going to use that function now. Our next task is to graph that function. You can use either Desmos or you can use your graphing calculator. I'm going to use Desmos in this case. Okay, so I'm showing you here our original function in blue. So that's this piece here. That's the piece that we originally put in, that we just talked about. That's our function. Now, how did I put it into Desmos? Well, I used y for the v of r part. And remember, that stands for the volume. So our y value is the volume. And then our r stands for radius. That's our x in this case. So notice how I typed it in. This is how you would want to type it in either on the graphing calculator, all right, like this, or onto Desmos or some kind of graphing utility. We want to use x there. So there's our function in blue. This is the same function right here. I'm just using x for r and y for v of r. So again, our y stands for volume, and our x stands for the radius. Now this is a cubic function because if I were to distribute this x squared to the x, I would get x cubed, or r squared times r, so I get r cubed. Again, that ties to what we're doing. And a cubic function is going to look like this graph down here at the bottom right. It's going to keep going forever. We're just going to look at a snapshot of the graph. So I'm going to put a couple arrows on this graph that I brought in over here to show you that this cubic function actually keeps going up and down forever. But we only want to look at the portion of the graph that applies to our problem. And then we'll talk about writing a domain and range for that problem. Okay, sometimes the hardest part for students is realizing they're okay with putting this in their y equals and then going to their graph to look at it, or a table. But when we get to go graph it, it won't show up on their graphing screen. That's because the students may have the wrong window set. So notice how my y-axis goes here from 0 to 10,000, and my x-axis goes from 0 to 20, or about there. Okay, so it really just depends on the actual problem. You just kind of have to do trial and error until you get a good window that shows up. Sometimes you can start generating a table. So if you go look at your table, and then you can set your window based on what you're seeing in the table. Great, so there's our graph. Now what we want to talk about is what we call a relative max. A relative max is going to be a spot on the graph that comes up to kind of like a top of a hill. Imagine a relative max is like the top of the hill. And down here on this graph, I've also indicated there in orange, there's our relative max. And the reason we call it a relative max is because this function actually doesn't have a maximum or a minimum. And I'm talking about the general function down here. Okay, you can see it keeps going forever up. So there'll be no there's no absolute max and no absolute minimum. So as you look at that, just think, okay, when I talk about relative max, I'm talking about just the top of a hill. In addition, we can also talk about relative minimums. I have a relative minimum right here in green, and you can see that over here in the bigger graph, the larger scale. Okay, so we talked about relative mins and relative max minimums. Okay, so let's focus in on this, what we call the relative max, because the problem's asking us to calculate the maximum volume for the tube given the constraints that we were working around. It also wants you to find the radius that gives that maximum volume. So let's interpret this order pair right here, this top of the hill. And on Desmos, you can just kind of click over to the top, and it normally will pick the relative max for you. Of course, if you're doing it on a graphing calculator, you can do the second trace features to find your maximum by doing a left bound, right bound, and maximum. Okay, so let's look at that order pair carefully. It's approximately 11.111, comma 6464. Okay, and remember that this piece right here is the radius. That's our x in this case. And this is our volume. Okay, so the maximum volume that you can get out of this is about 6,464 cubic units. Okay, and our radius that gives that is going to be 11.11. We don't need all these decimals here. 11.1. That's pretty approximate there. So as we look at that, we've answered the question. We have found the maximum volume given this constraints, and also the radius that gives that volume. So we've answered our question. Our last piece that we're going to look at is what is a reasonable domain and range. Okay, so you'll get the question that says, what's a reasonable domain and range? And normally that wants you to consider, the word reasonable wants you to consider the context of the problem. Again, when we look at this graph over here to the right, this thing keeps going up forever. So if I ask the question, what's the maximum, you would say it goes off to infinity in both directions. The reasonable part's down here, and the reason it's reasonable, let's think about this for a second. We'll make a little table, and we'll start listing some of these order pairs here. Okay, so some of the order pairs that we get here, 0, 0. Okay, and then we've got this 11, and just for shorthand, I'm going to just leave off the decimals here. Okay, that's that. And then we have another point over here. 16.7 about, and 0. Remember, this is a radius and this is a volume. So our x is radius and our y is volume. The reasonable part will be right in here. I'll highlight it for us. The reasonable part's right in there. And that is, as we move to the left, as we move to the left over here, our radius is negative over there. As soon as we cross that point right there, we get a negative radius. And a negative radius doesn't make sense. In addition, over at this point, we can't go past 16 and 2/3 for a radius because as we go down this direction, we get negative volume. And of course, that wouldn't make sense either. So our reasonable domain is in this highlighted part. So we'll say that our domain, remember our domain is from left to right, so in this case we're considering our radius, radii that work. So our domain, the radii, go from 0 up to 16.7. So the largest radius we can get, given these constraints, and remember the constraints were the height plus 3 times the radius has to equal 50. So we can't go above the height plus 3 times the radius above 50. So this makes sense for the domain. Now our range, in this case, is going to be volume. So volume. And our volume is going to live between the top and bottom parts of this highlighted graph here. Obviously, we can have a volume greater than 0, and we can go all the way up to 64.182. Okay, so we have a reasonable domain and range now. And again, I want you to, if you're having trouble seeing domain and range, think back to your Desmos project where the domain is your left-right bounds and your range is your up-down part. Now, this graph over here in red, over here, this one, the domain and range is all real numbers because it goes left forever, goes left and right forever, and it also goes up and down forever. So we would say, in this case, our domain and range for this one would be all real numbers for both domain and range. Okay, that includes our introduction to polynomials there, which has a nice word problem, building functions, graphing functions, talking about relative max and mins, also talking about domain and range. Hopefully that helped. Have a great day.